In GNU Linux and POSIX systems in general, the usual way for userland processes to communicate with the kernel or to make the kernel do certain things on its behalf is to do syscalls or system calls. Doing system calls is expensive. It is slow, relatively speaking. And it doesn't matter the nature of the operation that you ask the kernel to do. It may be complicated or it may be trivial. It is still slow. And this is a problem. So the kernel hackers some time ago, they added a new feature, which is a very clever hack, which is called the vDSO, for Virtual Dynamic Shared Object. How does this work? Okay, let's say that you have one of those operations. This is a very rough explanation, but and a very fast one, but it's just introductory. So basically, let's say that you want to your userland process needs to know what is the time, the current time. It needs a timestamp, which is basically a 32 bits integer with a unit date in it, which is the number of seconds is the 1st of January from 1970. Okay, so in a Unix system, if you want to know the time, then you need to ask the kernel for the time, because the kernel is the system component that has access to the watch, basically, right? So classically, you needed to do a syscall, and then the userland process will call to a glibc, to a libc function called getTimeOfDay, and the libc function getTimeOfDay will do a syscall to the kernel. But this is slow. Now, with this new mechanism, which is implemented by most, if not all, of the kernel ports nowadays, certainly the ones that actually matters, like x86, ARM64, RISC-V, MIPS, Spark, PowerPC, whatever. Then with this new feature, the process, instead of doing a syscall, it can directly do a function call to a function that is in this vDSO provided by the kernel, and there is no more the need to do a syscall, which is like magic, right? So how does this work? Okay, so the kernel, when it creates a new process, it fabricates a virtualize. That's why it's called vDSO. Is why it's called virtual. It fabricates a new DSO, which is a loaded. It's like a loaded ELF DSO. The loaded part is important. We will see later. And then it makes it available in a page which is mapped in the virtual address space of the process, of the userland process. So in the same way that in a userland process, imagine that in the userland process you want to call to a function that is provided by some library, lib JPEG, lib readline, lib whatever. What do? You have that the lib readline.so mapped, loaded in your virtual address space by the dynamic loader. All of this happens in userland, and then you just do a function call to that address, and then it executes the function code, the code of the function you are calling, which is loaded in some executable segment provided by the DSO, in this case libreadline.so. So if you want to call getTimeOfDay and you are running in a kernel that provides it in a vDSO, you do exactly the same thing. So basically, you execute your code, the userland process. It does a function call. Well, actually, it calls glibc getTimeOfDay, and then it is the glibc getTimeOfDay implementation that do a function call to some function whose executable code is in some executable segment provided by this virtual DSO. So you see how the tricks works, right? Okay, so in this short video we are gonna, and this time will really be short, I promise, we are gonna use poke in order to take a look to the vDSO of some running process in the system, because to look at the vDSO you need the running process, right? Okay, so the first thing we need is a running process. So we run a top command that will be happily running here, ignorant of its danger it will be, and then we need the process ID of this command, of this process, which is 3296. I'm writing this down, 3296. And then we are going to run our favorite program poke, and we are going to use the proc.command in poke to open this process. What does it mean to open a process from POC? Okay, so basically this command, when we execute it, is gonna create a POC IO space, which will be providing the access to the entire virtual memory address space of the running top process. So it's not gonna stop top, but it's gonna provide us read and write access to the virtual address space, which is quite cool. So let's do it. Now, those are the IO spaces that we have open now in POC. Now, the thing is, we have an IO space called proc, of type proc, which is the size is what you will expect for the virtual memory address space of a 64 bits process, which is 64 bits of bytes, basically. And it is currently selected. But we see that this .proc command also opened a set of sub-IO spaces. What are sub-IO spaces? In POC parlance, sub-IO spaces are IO spaces that basically provide access to ranges, to areas of some other IO space. So in this case, all those sub-IO spaces, they provide access to certain areas of the main IO space. And some of them, they have names. Well, they don't have names. Some of them memorable, some of them not that much memorable. Why? The .proc command does this because we specified the M flag, which is for maps, right? It's called for maps. Those things are called maps, right? Each in the system in GNU Linux. Now the thing is, now we have the proc IO space selected. If we dump the bytes from the offset 0 using the dump command, we get this. We get question marks. Why are we getting question marks? Well, because at offset 0 up to there, there is nothing mapped in the virtual address space of this process. So we need access, we need to find the interesting areas, and that is what those sub-IO spaces are providing to us. So what are sub-IO spaces we are seeing in this particular process? Well, we see some of them which they don't have memorable names. We don't know exactly what they contain. But some of them they do. They have memorable names. And for example, this is the heap. There is the heap of the process. There is the stack of the process. And the vDSO, which is what we are looking for. And the vDSO, we see that it is 4K big, which corresponds to 1 page in this x86 system. And it is the vDSO, it is in the sub-IO space that shows basically starting at that position in the main IO space. So let's switch to the IO space number 10, which is the one containing the vDSO. And let's dump the bytes. Okay. So this looks much better. Okay, first, as expected, there is stuff there, no more question marks, right? Second, it looks like an L file, which makes full sense. Why? Because the virtual vDSO, the vDSO is as DSO, and it is a loaded DSO, so it corresponds to an L file. It makes full sense. Now, in POC, we know that we have pickles and we can define our own data structure. So, and there is an elf pickle. So let's load the elf pickle, and in the same way that we will do with a normal file, we are gonna map an elf64 file at the 0 offset of the current IO space, which is the vDSO of the running process. And okay, let me put the page here. Yes. And okay, so we got, what do we got? We got an L file, which looking at it like briefly, okay, in the header, okay, 64 bits, blah blah, x86 64, and we see that it has a section header table, and it also has a program header table. Interesting. So this is one of those interesting cases where one L file has both sections and segments. Okay, so let's take a look like overall using the dump bulk command, which is one of my favorite ones. Okay, we see that we have the elf header here in red, then the program section, the program header, the program header table there in blue. Then some contents, which is basically the contents of the segments and sections, which can overlap. And we have the section header table down there at the end of the file. Nice. Okay, so let's take a look. How many? Let's take a look at the program header table. Okay, we have 4 of them. And the section header table, we have 16 of them, right? Well, actually not, because the first one is empty, so it's it's null, so to say. So we have 15 actually, not 16. Okay, so if we were interested, for example, let's take a look to the program header table, to the segments, because the segments is actually what gets used by the running process, right? Because it's the loaded segments in memory. That's where the interesting stuff is. Okay, so what do we have here? Okay, let me okay, so we have a segment which is executable and readable, and it's sort of big, right? So most likely the contents of this segment are the executable instructions provided by the virtual DSO. So this is x86 compiled instructions. Then we have a dynamic segment which contains information about the dynamic symbols, and also we have a node segment which contains ELF nodes, which are annotations with metadata, whatever. And finally, we have a GNU EH frame. So we have this segment which is only readable, that provides unwind info for the first entry, unwind info for the executable code, for the functions and whatever, right? Okay, so if we wanted to look around here, again we are using POC. So if we wanted to access the first the contents of the first segment, we could, if we had one, we could load an x86 pickle that knows how to understand x86 instructions. I don't have one at the moment, something that will be written at some point, but I could write one, certainly. If we wanted to look at the contents of this second segment, which contains dynamic symbol information or dynamic information for dynamic linking with this stuff, we could also use some POC pickle, in particular the ELF pickle. For the nodes, it's exactly the same, and for the H frame, we could use the DORF pickle that contains definitions that to understand the unwinding info, the FDEs, the CIEs, and so on. So let's take a look to the nodes, just for the sake of having a little bit of fun, very quickly. So we already have the ELF pickle loaded, so we can take a look. Okay, info types. What do we have for nodes? Okay, we have a type which is called ELF node. Now, this is a segment that contains ELF nodes, right? How many of them? Whatever fit in the size of the segment, right? So let's map them. So ELF node, a connection of them. Where are those nodes to be found? Okay, it is the nodes. It is the ELF PHDR. It was the 012. It was the number 2. Okay, where is the base? Where are them to be found? Okay, we can see here that there is a physical address and a virtual address. Well, and an offset. So basically, the offset is the offset in the file, in the ELF file. If this was ever in an ELF file, but it was never, because this is a fabricated virtual DSO. So this is a loaded DSO. So we should not be using the P offset, but we should be using the virtual memory address, because don't forget, we are poking at the virtual memory address of this process. So ELF PHDR2 .pvadr. So there. So how many ELF nodes? Well, whatever fit in. Again, there is the file size of the segment and the loaded memory size of the segment. So this is the mem size is the size of the segment that it occupies when it is loaded, right? So basically, in this case, it's the same, but it doesn't have to be. So p mem size. So here we are doing a mapping of an array in POC using a size instead of number of elements. And POC does its magic in the sense that if there are not an exact number of ELF nodes that fit exactly in this size, it will emit an error. So, okay, so there are nodes here. There are 3 nodes. So let's put it in a variable. So there are 3 nodes. So what are we looking at here? Okay, so the first node is of type Linux version code. Okay, ELF nodes, they have a name and a description, right? The name is by the standard. The name should be some sort of a string encoded in a sort of a not trivial way. That's why it's pretty printed. That identifies the provider of the node. So there is GNU for GNU extension nodes, but in this case, the Linux kernel uses Linux. So and then the description is basically a set of bytes. And it doesn't have to be a string. It doesn't have to be anything in particular. I mean, you should interpret the bytes in the description of a node based on what kind of node it is. So, basically, the first node we see that the provider, the originator, is the Linux kernel. So it is a Linux kernel specific ELF node, and the name is Linux version code, which looks like this should be some version code of the kernel, right? The second one is also the originator is also Linux, so it is a Linux kernel specific node, and the name is Linux build salt. And the third one is a GNU one, and it's called GNU build ID, right? Okay, so the ELF pickle, it provides an ELF registry, which is documented in the manual of the ELF pickle, that has an apropos function. And in the apropos function, you can actually ask for things, like, for example, what is a Linux version code? And then we get that the description, it contains an unsigned 64-bit integer encoding Linux version code. Okay. So let's take a look. Let's put the output numerical base to hexadecimal. So let's take a look. This will be an 64 bits unsigned integer at where? Okay, so we have the nodes here, right? Nodes. And we are interested in the first node, okay? And where? So at the address, at the same address that is used where this array of bytes is mapped, right? Because we want to reinterpret this array of bytes, right? So we use the offset attribute of this field or of this variable, of this value, right? So we get that unsigned integer, which, is not very interesting. But again, this is POC, and it happens that there is a Linux pickle, and the Linux pickle now it's okay. The Linux pickle now I just started it, so it just contains this. But let's say that it will contain more stuff. So the Linux pickle, Linux.pk, it has definitions useful to access to poke at the Linux kernel data structures, right? So we are interested in a version code, right? So we could say something like info types Linux version. There is a Linux version code struct type declared in Linux.pk. So let's map it. Instead of an unsigned 64 bits number, let's map a Linux version code. And we get one pretty printed to 510.158. Okay, so this is basically, it has to be a Linux version encoded somehow, right? So, and this is the content of the first node. Okay, let's look at the second node. The second node is a Linux build salt. So what is this? Okay, so elf config apropos Linux build salt. Okay, arbitrary string to avoid identical vDSO. I thought this was a typo. vDSO debug info. Okay, well, it says arbitrary string. Okay, so likely, if we map a string at that particular position, now is this the second node, right? The offset of the description. Okay, we see this 510.0.20 AM 364, whatever. Okay, so it happens that this Linux build salt is here because imagine that you have one particular version of the Linux kernel. So this particular version of the Linux kernel for this particular architecture, let's say for x86, it fabricates one vDSO that makes available to all the processes it runs, right? As we discussed already. Now, as you know, as you may know, the debug information provided by distros and used by debuggers and everything, basically the debug information is based on the object it is describing. So that's how you associate some particular debug info to which may be in a separated DORF or something, a separated object to some particular code. But if you have two different Linux kernels, different versions of the kernel, that happen to provide the same vDSO, the vDSO would be identical in both cases. So there will be a conflict. Well, not a conflict. There will be a collision, right? Because basically there will be no way to separate both, to dissociate both, right? To know that the vDSO, this virtual vDSO, comes for different versions of the kernel. Anyway, thing is that it's problematic. So to make the vDSO not identical and to make it unique, to be different for every version of the kernel, then the kernel actually inserts this node, this elf node, with this string. And then we have the last one, which is a GNU build ID, and then it is GNU build ID that it says contents are not required to be printable and it's opaque. And in fact, if we try to map a string at there, in fact, it's actually not printable. I don't know exactly what is the kernel because this is created by the kernel. Well, actually, it could be created by GCC if what the kernel is doing is to compile the vDSO, so the DSO before being loaded separately. I don't know how that works in the kernel. I will need to go and look. But anyway, it's not printable, but we don't care. So, so this was it. I mean, basically, we looked around and we saw that we looked at the different nodes of the vDSO in the running process. Now we are done playing around. So what do? We close the IO spaces. Now in POC, if you can close individual sub IO spaces, but if you close an IO space for which there are other IO spaces which are sub IO spaces, then the sub IO spaces gets closed too. So if now we close the IO space 0, all the others are closed as well. And we can get exit POC, and here we see the top command is still happily running around. Okay, so see you next time.